Long ago, in an early algebra class, you had your first encounter with binomial expansions when a teacher asked you to expand an expression of the form x plus y squared. This was probably confusing to you until Mrs. Neese explained that x plus y squared just means x plus y times x plus y, and you could use the principle of distributing multiplication over addition. So the first term in the first factor, x, gets distributed to both terms in the second factor, giving you x squared plus xy. And then the second term also gets distributed to both terms in the second factor, giving you xy plus y squared. And then you combine the like terms in the usual way, and you get the familiar answer x squared plus 2xy plus y squared. Well, you practiced this a lot, and you probably considered yourself to be an expert at expanding binomials until you got to a later algebra class where a different teacher asked you a more difficult question. This time, you were asked to expand the binomial x plus y to the ninth. Now, you probably were shocked at first, thinking that Mr. Ruhr wanted you to write out 9 factors of x plus y and then distribute multiplication over addition. And this would have been a lot of work. But Mr. Ruhr had in mind a simpler process. What he wanted you to do was use Pascal's triangle. It's a clever trick where you write 1 in the first row and 1, 1 in the second row. And then you continue generating the numbers in each successive row by adding up the numbers above it. So for example, 15 plus 20 equals 35, and 21 plus 35 equals 56. And if you write out Pascal's triangle to the row that starts 1, 9, 36, 84, then you get all of the coefficients of the terms in the expansion of x plus y to the ninth. 1x to the ninth plus 9x to the eighth y plus 36x to the seventh y squared, and so on. You get all 10 terms in the expansion of x plus y to the ninth. And it's much easier than it would have been to write out 9 factors of x plus y and distribute everything and collect all the like terms. Pascal's triangle is a nice trick that makes it easier to expand binomials raised to higher powers. And after you got good at using Pascal's triangle, you probably felt like you were really an expert at expanding binomials. You may have felt that way until you reached another class at a higher level where you were asked a more difficult problem. This time you were asked to expand the binomial x plus y to the 100th power. And you might have said to yourself, how could Professor Wagenheat expect me to write out Pascal's triangle all the way to the line that starts 100? That's way too much work and too much paper. But actually, Professor Wagenheat has another trick in mind that will make the problem simpler. And to explain that trick, let's take a look at the pattern in one row of Pascal's triangle. If we look at the ninth row, we see that the numbers in the ninth row are actually the combinations. 9 choose 0, 9 choose 1, 9 choose 2, 9 choose 3. This comes from combinatorics. The pattern is that the factors in the numerator are descending and the factors in the denominator are ascending. If you don't recognize these numbers as the combination, for example, if you don't recognize this number as representing 9 choose 3, try rewriting it in the usual way using factorials, and you'll see that it's the same thing. If we know that these numbers are combinations, then it's easy to generate a list of the numbers in any row of Pascal's triangle. You simply multiply by descending factors in the numerator and ascending factors in the denominator. So for example, you start with 1, you multiply by 9 over 1 to get 9, then you multiply by 8 over 2, then you multiply by 7 over 3, then you multiply by 6 over 4, 5 over 5, 4 over 6, 3 over 7, 2 over 8, And when you multiply by 1 over 9, you get back to 1. And you could generate any row in Pascal's triangle by that pattern of multiplying by factors where the number in the numerator is descending by 1 and the number in the denominator is ascending by 1 each time. So Professor Wakenheed means you to use that to figure out the numbers in the 100th row of Pascal's triangle. So you start out with 1, coefficient of x to the 100th is 1. Then you multiply by 100 over 1, and you get the next term, 100 x to the 99th y. Then you multiply by 99 over 2, and you get 4,950 x to the 98th y squared. And then you multiply by 98 and divide by 3. And you get the next term, which is 161,700 x to the 97th y cubed. And you keep on doing that, and you get a very long binomial, but you have, with relatively little work, expanded a binomial raised to the 100th power. And now you might feel like you're really an expert at expanding binomials. That is, until you get to an even higher level course, because now you have a teacher that asks you to expand an expression of the form x plus y to the 1/2 power. You might not even recognize at first that that is a binomial being raised to a power, because it's written with the radical symbol, but remember that the square root of a number is the number raised to the 1/2 power. Well, before you panic and run away from the problem, let's try to understand what Monsieur de la Saussure wants you to think about when you see a problem like this. Let's go back and look at the problem that Mr. Ruhr gave you, problem of expanding x plus y to the 9th. Your new teacher wants you to look at x plus y to the 9th in a slightly different way. First, you take x plus y and you factor x from it, so that you have x times 1 plus y over x raised to the 9th power. Next, you're going to make a variable substitution. Let u equal y over x. So you get x to the 9th times this nice function of u, 1 plus u to the 9th. And this function is very simple to differentiate. So let's find a Maclaurin series for this function. And the way you make a Maclaurin series is you make a table with 3 columns. And in the first column, you write down the function, and then its first derivative, which you find using the power rule, and then the second derivative, which you find with the power rule again, and the third, fourth, fifth, sixth, seventh, eighth, ninth derivative. In the second column, you evaluate all of those functions at u equals 0. And again, it's very easy to evaluate them at u equals 0, and you get a series of numbers with descending factors. And the next column, you find the coefficients in the Maclaurin series by dividing those numbers by the factorials. And what you'll notice is those coefficients have the same pattern that you found in the numbers in Pascal's triangle. They have descending factors in the numerator and ascending factors in the denominator. And the great thing about that is that this pattern came from the power rule, and it did not come from combinatorics. That means we can use that same pattern even when x plus y is raised to a number that's not a positive integer. We can now raise x plus y to any real number and use the same pattern to expand that binomial. So binomial expansion can now be used for things like square root of x plus y. We start out by factoring out the square root of x and write it as the square root of x plus times 1 plus y over x to the 1/2 power. And then we use this rule. We start out with 1, and then we have 1/2 times y over x, and then 1/2 times 1/2 minus 1, and then we divide by 2 factorial, and then we have 1/2 times 1/2 minus 1 times 1/2 minus 2, and we divide by 3 factorial, and so on. And we actually can get an expansion for square root of x. So let's write out the general form of what we're going to call the binomial series, because after all, this is an infinite series, and the general rule is 1 plus x to the n is 1 plus nx plus n times n minus 1 over 2 factorial x squared plus n times n minus 1 times n minus 2 over 3 factorial times x cubed, and on forever. And the pattern is clear, so you can see how to continue this forever. Memorize the binomial series. First, make sure that you understand it by applying it to the simple cases you've already explored, like 1 plus x to the third power. Using this formula, you get 1 plus 3x plus 3 times 2 over 2 factorial x squared plus 3 times 2 times 1 over 3 factorial x cubed plus 3 times 2 times 1 times 0 over 4 factorial x to the fourth plus 3 times 2 times 1 times 0 times negative 1 over 5 factorial x to the fifth. And you can see that although this pattern goes on forever, we're going to always have a 0 in the numerator. So it really does truncate. There are only 4 non-zero terms, and they come out to the familiar 1 plus 3x squared plus x cubed. And then let's take the case of 1 plus x to the negative 1, which is 1 over 1 plus x. And we see that the descending powers start from negative 1, so we never go through 0. So this series does not truncate, and we get an infinite series that turns out to be alternating in sign, and in fact it is the familiar Maclaurin series for 1 over 1 plus x. So once you've applied the binomial series formula to a couple of cases you're familiar with and convinced yourself that it works, let's try using it on real problems. Suppose, for example, you are asked to take the number cube root of 7 and come up with a decimal approximation using the principle of binomial expansion. Remember that when you learned about Maclaurin series, you looked at them as an extension of the idea of linearization and a way of coming up with a numerical estimate for numbers, where the more terms you calculated, the better an estimate you got. So we want to find some kind of binomial expression for the cube root of 7 that can be expanded. Then you see if you could work out a few terms of the binomial expansion and get a good rational approximation to the cube root of 7. Can you figure out how to do that? The key is to recognize that 7 is 1 less than 8, and you already know the cube root of 8. So if you rewrite cube root of 7 as the cube root of 8 minus 1, and then you factor 2, then you get an expression that is of the form 1 plus x to the n, where x in this case is negative 1/8 and n is 1/3. Now you can use the binomial formula to find the expansion of this expression. See if you can find the first 4 non-zero terms. Pause the video and try it on your own and see if you get the same result that I'm going to show you now. Since n is 1/3, we're going to be multiplying by 1/3, and then 1/3 minus 1, and then 1/3 minus 1 minus 1, and so on. After the first, those are all negative numbers, and we're also multiplying by an extra factor of negative 1/8 each time. So it turns out that after the first term, every term is going to be negative, and when you simplify the expression, you get 2 minus 1/12 minus 1 over 288 minus 5 over 20,736. And if you understand how to find approximations like this using binomial expansions, maybe you really are an expert at binomial expansions.